Chapter 3. Chapter 3 is about introducing you to a couple more operations or operators on the fundamental data types. Essentially, you got the data, the kind of data you deal with, and now we are learning what we can do with them. Of course, we've seen examples of them, but let's take a look at a couple more. So first thing is that when you have multiple operators in an expression, then there comes the issue of how to evaluate that expression. If you, uh, let's say, don't use parentheses to uh, make your intentions clear, although I usually advocate that's what you should do. But in some cases, it's obvious that everybody knows, and then you don't need to use parentheses. And this is very much natural to what you learn in math. So one concept is a precedence. So some operators will take higher priority than some others. When that is the case, they would be evaluated at first, unless that evaluation is overwritten with the parentheses. And then when you got parentheses uh, around terms, and then those will get evaluated from innermost parentheses to the outermost. So this is nothing new here. And then if you got a multiple operators at the same um, in the same place next to each other, and then there comes the issue of associativity. Um, so basically, whether you're going to evaluate the expression from left to right or from right to left. So that is the concept of left associative or right associative. And actually, good news is most of the operators are left associative. And here's an example, right? So you have, x multiply y divided by z minus b plus c plus d. And the evaluation order, if I don't add in any parentheses, like what I've done here below, that's what the effective evaluation order is, right? You kind of start with x multiplied by y, you get a result of that, and then divide that by z, right? So that is because the precedence and associativity rules. And so there's no surprise here because this is what you probably have learned in math, right? Multiplication and division, they have the same precedence, but they also have they are left associative. So basically you evaluate from left to right when you have two operators next to each other like this. And then here's a table of most of the operators that you're going to see in C++. And we have encountered a couple of them so far, such as here, for example, the postfix increment and decrement. And then as you notice that the precedence of a postfix increment and decrement is different from the prefix form of those two operators. And so the postfix form uh, takes higher precedence than the prefix form. Okay, so and then we have other things that you encounter so far. For example, this is where the multiplication division lies, and then with also modulo operator, and of course yeah. So and then we also have seen the assignment, right, and a compound assignment introduced in the last chapter. So, and then there's a bunch of others that if you're not familiar with, we're going to learn most of them as we go along this course. Now, the other type of operators deal with bits in a number. And so they are called bitwise operators. And then let's take the first things that we're going to look at is the shift operators. We have, you remember the last table that we have introduced in the last chapter where you see this stream insertion, stream extraction operators, right? Those double greater than, double less than symbol. They are also used in the context of a bitwise operations for shifting numbers. What does shifting mean? And let's say we declare a unsigned short integer that's typically 2 bytes, and then we're going to do a left shift operation. So in this context, it's very clear to the compiler we're doing a bitwise shifting because We don't see a stream operation around here. So there's no ambiguity. That's how the compiler determines. If it cannot determine, then there could be an issue. So the compiler probably giving an error. So the bitwise shift, what really happens here, so let's take a look. Well, before we take a look at what's happening with the number, and you may wonder, okay, why do we need to do a static cast here to back to unsigned short? I mean, isn't number already unsigned short? Well, that's because this literal number here too, right? So if you have no, and by the way, there's no literal for a short. So if you've in the book, right, talk about the suffixes to uh, designate a literal number to be, a integer, a long integer, or long integer, right? So when you see a number like this without any suffix, this is actually determined to be an integer type, is an int. It's actually an int. So, and then also because the rule, when you have different mixed types of data in an expression, the compiler needs to elevate the lower range type to the higher range type. So the compiler would probably do is to actually cast this unsigned short number to an int, and basically and then perform this operation, right? So that's and then so basically, and the result of that, uh, the result of this expression is going to be just an int. So that's why we need to cast that back to unsigned short. If your intention is to get back unsigned short in that result. So the book explains about auto keyword, and then so I just kind of mentioned this thing here. What you're going to see auto quite a bit later on, not as much right now, but the auto occasionally, if the book uses this, again, the book has explained. If you read the book in the proper order, and it will explain everything. So it's the auto really here means to tell the compiler to, okay, I'm basically as a programmer, you're telling the compiler to deduce the type of this variable you are uh, declaring and initializing, okay? And then we're initializing the result variable with this expression, which obviously we have casted or converted back to an unsigned short. So obviously, right, the type of the result is going to be unsigned short. So that's what the compiler will figure out. So that's kind of saves you typing. And so the auto here, basically that's what this is. Okay, so what's actually happening with the shift operator? In this, the decimal number 16,387 in binary is this, right? And then to shift left, this is, again, this arrow kind of a shape, and then it's very intuitive, it's shift and left. And shifting left by 2 bits is what this number 2 means. So what's actually happening is that we're going to shift all the numbers to the left. Okay, and then you think what's going to happen to the ones that were shifted out? Well, the most significant bits are going to be just discarded. So you see, we shift 2 bits to the left, and then the 0 and 1, they are shifted off of that basically these 2 bytes of data, right? So they will be just simply discarded. And then to the right, once you've shifted, now you got 2 empty slot, right? There's bits, and what's going to happen? You fill in with the zeros to the right. So that's what's happening here, okay? So you see all these bits shifted to the left. Now, because this binary, the binary calculation, it's a pretty straightforward. And what's happening, right? Whenever you shift to the left, it's a straightforward. Basically, then every bit in the original position now gets multiplied by 2. Essentially, the order in that calculation, right? So here, if you calculate the number, this is basically 1 plus 2, right? 1 plus 1 times 2 to the power of 1, right? Plus 0 times 2 to the power of 2, right? But again, this is going to be 0. So that's what really, if you write out to determine the decimal value of this binary number. And so when you shift to the left, every position for that bit gets basically multiplied by 2. That's really what that ends up being done. So essentially, shifting to the left is equivalent to multiplying by 2 to the power of that number of bits that you're shifting. And again, this if in the book there is a typo or an error. I've actually when the book says a 2 times n, but actually 2 to the power of n. And then that is actually also put in the manual. If you take a look here, there's a section textbook errata. And then so I have stuff here. So I'll be adding some of the errors in the book in here as I spot them. Okay. Or if you have noticed something, let me know. Okay. Now back to the slides. So and by the way, the other direction, obviously, what I have not explained here, so I'll leave this to you to read the book. And shifting to the right is equivalent to division, right? So it's dividing by 2 to the power of n. And then when you shift to the right for unsigned number, the most significant bits will be filled in with zeros. Okay, of course, when you shift to the right, the least significant bits will be dropped off, right? Or discarded. And if it's a signed number, now if it's a signed number, usually the the highest order bit is a 1 to signify the negative number, if it's a negative number. And if you're shifting to the right, and then what you fill in to the empty bits, when you're shifting to the right, they will be the same as the sign bit. If it's 1, and then you will fill in with the ones, okay? And then the bitwise operators not only will have the shift operations, we also have the logical operators. And so the logic operators, and here's basically the 4 logical operators on bits. So you have the bitwise complement operator. What a complement means that if that bit in your original number for that bit, if it's 0, now it becomes 1. If it's 1, it becomes 0. That's what a complement operator does. And then you have the AND operator. Okay, AND operator means that if you, again, this is a binary, and by the way, this complement operator is a unary operator. It means it takes only 1 operand. And then this AND operator is a binary operator. It takes 2 operands, one on the left and one on the right. And so for the same position of the bits, if they are both, well, actually, when it's AND, it means if either one of them is a 0, it'll be a 0. Otherwise, it'll be 1, right? Or same thing, if both are 1, then the result is 1. So the only scenario with the AND operator for the result to be 1 is they're both 1s. And here we got the exclusive OR operator, or XOR operators. XOR operator is it's kind of strange, but it has a very important usage in the language, of course. We'll see in a bit. And this XOR operator, it means that it's going to compare the 2 bits from the 2 operands. This is also a binary operator. So it compared the 2 bits if they're the same, the result is 0. If they're different, the result is 1. And then you've got the bitwise OR operator, which is a pipe character. And well, by the way, if you're familiar with logical operators, not the bitwise, just regular logic operators, you see a double ampersand, right? Double ampersand, that's for Boolean operation. And there's an analogy there. And then you also have the double pipe. That's basically the Boolean OR operator, right? This here, we're talking about the bitwise operator operating on bits. And so the OR operator, if they are basically, if any one of these two bits is 1, and the result is 1, otherwise it's 0. So hope this is kind of fairly easy to remember, and if you're not, come back and review this when you're programming. You'll get used to this. Okay, so what is the usage of those things? Now, typical uses of the bitwise operations is about manipulating flags. What's a flag? For example, your compiler has a lot of flags. And the flag usually means you have something that's on or off, like a switch in a house. And so it's a binary. It can be efficiently represented as a binary bit, right? It's a bit. So you don't need a whole int to represent a flag that's basically just on and off, right? So this makes it efficient to compact, put multiple flags together and manipulate and then just record the state of flags. And so there's many usage of this. The book also explains obviously other examples, and we're going to look at the example just very shortly as well. And this bitwise AND operator usually is used to select the bits, and also can be used to turn off a flag. And then this OR operator is to turn on a flag. And then you have this XOR operator. XOR operator, it's used to toggle a flag. If it was, essentially if it was a 0, you can toggle it to 1. If it was a 1, you can toggle it to 0. And then you have this bitwise complement operator, which is actually used to generate a mask for the AND operator to basically like turn off a flag. And so that was a mask, right? So we're going to see this in this example here. Let's take a look at this example. And suppose we have, so basically this is the example 301. And so we declare two variables here and a const. Now again, so as I mentioned, if your variable is meant to be a constant, add this const keyword here to make that intention clear. And so if later on somebody or some code, if you're working with a team trying to modify that variable, the compiler will balk at you, okay? And that's what you want. So you have this unsigned int. So again, actually, just a little tip, when you're dealing with bitwise operation, using the number to store flags, you usually want to deal with unsigned because there's no purpose of that sign in the number. So just might as well use that bit for your purpose, right? So here we have unsigned integer red and white, and this is actually an example of of a color, RGB color. The red, green, blue type of encoding for a color, and that's also pretty common in the web-based programming, right? And so a color red is that you have those positions in the first byte. Well, actually not the first, but the most significant byte. Let's say you have RGB in that order, right? So by the way, this OX prefix, that's a hexadecimal notation. And then you see this literal, we have a suffix here with a U. And the U indicates is unsigned. So when we initialize the unsigned integer red with a literal, we also want to make sure that this is unsigned integer, and we don't. So essentially, that goes back to the principle of making your attention is clear, that I keep repeating, and don't let overly rely on the compiler behavior of converting your, uh, doing the casting on your behalf, right? So if you know what you're doing, and that's what is usually preferred. So the you got this is the red color, and then if you got the white color, so you have all ones in all the, yeah, basically 4 bytes. Okay, so a single hexadecimal character represents 4 bits, right? So you got actually 3 bytes, sorry. So you have 3 bytes here, and then the fourth byte you're not using. This is using integer to store it, so you kind of wasted 1 byte. The book also indicates sometimes you need to store the alpha value of a color, then you may use that for it. But anyway, as in this example, we're just dealing with this RGB 3 colors here. So okay, you also see some examples of formatting, and so I'm not gonna repeat what we just discussed, and then you should be able to understand what this means now, right? So again, 0, right? You know what this means. 0 means that for this number, you're gonna fill with the zeros when you're doing the alignment in that field of width. Again, well, not the this is actually not the yeah, it is the width is 8. So actually, let's run this. We're going to see this is the result right here. So we have defined the width to be 8 digits, 8 characters. Okay. So as you see, when we print this out red, this is actually, we're printing out the whole integer number, which actually is 4 bytes typically. And so besides what we initialize with, FF000, right? And the got 0 in the front of it. And so anyway, so the important thing here, we're talking about the bitwise operators. So the first thing is we illustrate is the complement operator. So the complement operator basically turned zeros to ones and ones to zeros, and then see this, right? So it was 0, now it becomes F. F means they have 4 bits of ones. They're all ones. Okay, so that's what you see here with a complement. And the same thing with Y. So Y used to be a 0, 0, all Fs, and then now you got FF, all zeros followed. And now the next one is about the bitwise AND operator and OR operator. Okay, so what's happening again? So this just illustrates what's actually happening. And when you do the AND operator, so take a look at this red and white, okay? Focus on these two things. And when you AND them together, so the only case for that bit to be 1 would be both have to be 1. So you'll see the result of that AND operation, and then you got basically you see the result. You got the ones over here, and zeros everywhere else, and then there's also ones over here in the same position for white. So these are the two only ones in those positions of bits, right? So that's the and then you got the or. Or means if you got one of them is 1, and then you got a 1. And so if you look at this again, and then so take a look at the Y, you have all these FF, these are all ones, and so the result of those bits are going to be all ones. And now what happens to the top 0, 0? Again, this is the bits that we did not use when we defined them, so they could remain to be 0. They're both 0. So you see this. All right, and then let's talk about a mask. Mask really it's a mechanism, is another number that we generate so that we can actually perform, for example, operations to retrieve the status of a flag in that number, right? Thinking of a flags putting into a whole number, many flags in a whole number is like encoding. And then so we have a way to retrieve it with the help of a mask. And we also have a way of modifying them, again, with the help of a mask, okay? So that's why the mask is going to be kind of an integral to this whole, flag usage with the bitwise operations. And so here we define a mask with the XOR operation between red and white. Now we know, okay, actually, by defining this mask with XOR operation, so previously in the slides, we'll talk about this XOR is typically used for toggling purposes. Now, what turns out to be really good at is that once you have a flag with XOR operation, then you can actually recover one of those two values when you basically so that's what's happening here. Okay, then kind of the example usually says it best. So XOR operation of red and white. So the result would be one if they're different. And so you see the only parts that are different with is the last four groups of hex characters, right? So that's why the only last four becomes F, right? So you have 00 and FF, and then the result of that is going to be ones, so they're FF, but then the other portion are going to be all zeros because they're the same, okay? So we explained how that thing works. So when you apply a mask over the one of the operands of XOR, you apply that result back with one of them, again, you get the other. So you see mask XOR red, what you get is white. Is it the same as white? You mask XOR white, you get red. Okay, it's interesting, right? And in fact, because this property, you could potentially use this mechanism to do a disk backup. You have two disks, and then you have a backup disk that stores the XOR results of the disk one and disk two. And then if you lost one of the disks, then you can recover the other, right? That's kind of an idea here. So, and then let's take a look at another usage here. Let's look at the selection and the modification of flags. So let's say we got a flag variable here. We're gonna use essentially just a bits here. And then we have defined a couple of masks. Again, the operations on flags. So you gotta, how do you pick those bits, right? So you need the help of mask. So let's see what happens. Let's say I have a mask that has a 1 at the bit position. Well, this is actually the bit position, actually the last, the least significant bit, right? And then of course when you write just a 1, this is actually a hexadecimal, and then all the rest above this 1 are zeros, right? So by doing this, let's say you're gonna select, you want to select that bit, the in the rightmost bit, and then you basically, whatever value of flags right now, you use this bitwise AND operator, and then you can actually select that value, right? So why is that? Well, if that original value here was a 0, when you use the AND uh, operator, the result will be 0. And then if you use if the original was 1, and then with this and this position is 1, so the AND operation will give you 1. So it will give you the value of that 1 bit in the flags variable, right? And then, of course, once you got that value, then you can print it out, or do something. You can check if it's a 0 or 1, okay? And then perform operations accordingly based on the flag. So if you want to select this, we're going to just count from the right hand side to the left. Like you have got 1, 0, basically 1, 2, 3, 4, 5, 6. Let's say you got the bit 6 as 1. That means you want to select the value from that flag variable at this position, and then you can get that value out of it. Okay. So what happens is, let's see, the result of that is that that's also the 6 bit is also a 1, right? And then by the way, so we're printing out, let's take a look at this. We're printing out hexadecimal format, right? So again, that position, in the sixth position, so again, this is a hexadecimal number. You got, basically, if you see a number 2 here, that means it's 0010, right? The last 0 means 000 in the binary format. So that's exactly the 6th bit, which is also 1 because of, look at all the flags originally all 1s, okay? Okay, so you say, okay, once I got this, how do I actually get the value of 0 or 1? Okay, it's in the 6th position. Well, simple. You shift to the right, okay? You shift to the right 5 positions, and then you'll get the 6th position. And because that becomes this position that's in the 6th position, counting from the right, will be put into the lowest bit. And then you know it's a 0 or 1, right? So that's what you do there. And then what if you want to select the bit 20? Well, you could write out all the zeros to have that bit in the 20 position to be 1, or you can use the shift here. See, the shift is, it helps out, right? So, and then so basically you were shifting to left 19 positions, and you put that one in the 20 in the position 21, the bit 20, sorry. And so that's what you can do here to generate that mask. And then you can do the same thing here. Obviously, you can have a 1 left shift 5, right? If it's just a few number zeros, maybe you write it out or maybe not. And now this prefix 0b means this is a binary number, okay? By the way, if you got too many zeros here, you can't count, you can potentially put just a single quote in between, to separate them if you want. That's allowed in a number literal. So now the third situation here, as I said, well, you can switch off the flag. Let's say I want to switch off the flag on the position 6. I don't really care if it was on or off. Now I just want this to be off, right? And so what you do is you use this AND operator together with the complement. The complement, so here what we'll do is we'll turn that position, the 6th bit, to be a 0, and then the rest will be 1s. So when you do the AND operator, in that 6 bit, if the original was a 1, now it becomes 0. If it was original 0, it's still 0, right? So that's how you switch off that flag. And then you can also switch on a flag using the OR operator. And so simple, right? So using the OR operator, if it originally was 0, because your mask contains a 1, and it becomes 1. If it was 1 originally, now it's still going to be 1. So that will switch it on. All right, so that's the bitwise operations. Now let's take a look at another thing about variables, is the scopes. We actually have seen the scope, we just didn't really explain. The most common scope that you are seeing so far is called a block scope. Now, what does that mean? Now remember this main function as the entry point of your program. So I define a variable a here, and then the scope of a means starting from here, the code within this block, which defines the function of a main. So behind this, sort of lexical order, you can access that variable a. It's about visibility of the variable. Can you access a? Can you read it? Can you modify it, right? So you can use that a afterwards, because the scope of a is within this pair of braces. And of course, it cannot stop before it is defined. So it starts or declared. It starts from here, from the point where it's declared. And So obviously now you can do a prefix form of increment as example here. Now we see another pair of braces here. It actually starts a new scope. It's another block scope, which is nested inside the outer block, right? So this is its own scope. If you define a new variable here, int a here, then the second a right here, this is the scope of this a. So outside this block, you cannot access this a anymore, okay? But you can still access the a outside, which is in the outer block. And as an example of that a is the scope of that a here maintains within that block. If you try to access it outside that block, you cannot do it. That you will get a compiler error, like what's shown here. Okay. And here's a illustration of the actually the global scope, so-called. You declare a variable here outside of any blocks. Okay, it's not inside this is your whole program. And then this is your main function here. You've got some other function here. We're going to talk about function later on. And then you define declare a variable, a global variable here. Let's call it a global variable because it's outside any of the scope. So this name verb value one is in a global namespace. And okay, what does that mean? Well, that means that, for example, value one, you can use value one inside anything that's after that declaration. Not before, but after its declaration. This is the locus of a declaration. This is where the scope starts for that variable. And of course, inside the main, this we already seen, and then you declare another global variable value 4. Okay, the value 4, now, of course, you can access value 4 starting from the point of declaration all the way to the end of the program. Okay, as shown in this drawing here as the scope of value 4. Okay. There are actually more scopes beyond just this block scope and global scope, global namespace scope, actually. There's other things, the global, beyond those two. So you have for example, the function parameter scope. You probably know that the main function, the entry point function, that actually can take parameters. For example, when you pass arguments to your program, when you launch the program, right? So you can take those will be all the parameters of the main function, and then they will have this its own scope, but that scope remains within that body of that function. And then you have namespace scope, but we're going to get to those. We'll learn about namespace more, and the class scope, enumeration scope, and also template parameter scope. We're going to actually learn all of them later on. The other concept of variables, not just the variables, actually, even your constants. There's a so-called thing called the storage duration. Now, what's storage duration? Storage means the storing the value inside of memory. That's what the storage is, not into the hard disk or somewhere else. Memory storage. Storage duration, there's like, okay, this value or object, okay, every value in the specific program, you can, that's basically, you can call it as an object. If you got an integer as an object, is a little different from if you have an object of a class. Right? We're going to talk about class later on. But again, they're all considered objects. And that object has a lifetime, means it does not, well, what is the, when, basically, when does it enter into life, and when does it just disappear, get destroyed? And then we're talking about, this is the storage duration. And so I have 4 kinds of, this is actually, there's only 4 kinds of storage duration in the C++ program. You got it automatic. We have seen most of the variables that we have seen so far, they are automatic, in the examples, but they are, if you declare a global variable, by default, it's going to be in a static storage duration. And then there's also dynamic and thread storage duration. We're going to talk about them later on. Now, let's take a look at these two things. Well, actually, I'll just have a little brief introduction here. So let's actually take a look at this on the right-hand side. This is, it's called the process address space. Uh, So remember, when you compile your program, you actually generate so-called object files. And the object files, remember that how the compiling linking process work. And the object files get linked together to form your executable. They are arranged in a certain format in your file. And inside that file, the object file, which gets loaded into memory when you run your program, or the final executable file, which resembles the object file. It's just that you have more information there, such as linkage to other programs or library modules, for example. So you're going to have different sections of that file. And when you get loaded into memory, and that's arranged in sort of more or less this kind of simplified format, you got different regions of the memory for your program. So for example, this section, it's called text. And this is actually where the machine code of your program resides. And then you got the data section. This is actually where the static initialized static variables and global variables reside. And the BSS is it's basically uninitialized static variables are put in here. And then you have this dynamic portion of it. This dynamic portion, in some programming languages, if for example in Java, they may call this the heap, right? You've probably heard of this. And then in C++, the term we typically call it, it's called the free store. This is the portion, actually this can grow or shrink as needed. Essentially, basically, that's why it's called dynamic. When you have a object that's you basically created an object on a dynamic in a dynamic fashion, and then that object gets allocated and deallocated. Basically controlled by the program. And so this region of the memory kind of grows and shrinks. And then the other regions of this here below, actually, they are static. They are not going to change. And then the automatic, this is actually where the dynamic variables are going to be, or objects. And then, so we have seen the static goes to these two places, right? And then the automatic, all those variables are basically allocated on the stack. Now we're going to study this data structure a little bit later. And then this stack region or section of this memory will shrink or grow as needed. When you invoke a function, your automatic variables will be allocated on the stack. When your function call returns, they will be deallocated automatically. That's why it's called automatic. It's automatic storage management. That's really what that means. All right. Okay. So let's actually go through a couple of items, to summarize this chapter. The bitwise operators are necessary when you're working with the flags, as we've seen that example. And the single bits that signify a state, that's called a flag. Now, by default, a variable defined within a block is automatic. Okay, we have most of our examples so far are like that. And the variables defined outside of all the blocks have a global namespace scope and a static storage duration by default. So in the previous example image there, so for example, you declare a global variable like this, value 1, and that by default is going to be in the global namespace scope and also a static storage duration. The static storage duration, what does it mean, really? From the point you declare it, it's going to live on until your program exits, until your program terminates. That's how long that variable will live. Now, I did not have an example here, but this is from the book. I just kind of explained this a little bit about the enumerations. The enumerations, the C style enumeration with the enum keyword. That's the C style, but in C++, it's preferred to use the enum class declaration that's called a scoped enumeration or a type safe enumeration. And the way to access the enumerators, right, the labels basically that you declare as the possible values of your enumeration, you need to use the type with the colon, which is the namespace, which is the resolution, scope resolution operator. Um, and you may have noticed that in that, remember that table of precedence and the precedence table for the operators, that scope resolution operator is at the very top. And so that's useful for presenting fixed sets of values such as weeks, days of a week, um, or color names, right? And then there's another thing that it's also explained is the using keyword. You may have seen this so far, but this using keyword has many uses. This is, uh, for example, you may you introduce the entities in a namespace into your current uh, program. And by the way, this using depends on where you're declaring it. It's going to follow the scoping rules. We're talking about this global scope, right? You have the block scope. It depends on where you're using it. All the names that are available in this namespace, you don't have to use the namespace colon inside that scope only where you are using this statement. And then using, if you use a namespace and then colon a name inside that namespace, like some kind of entity, that's say a type name or a class or a variable in that namespace. And then basically you're bringing that name only, not everything in the namespace, but only that name. Now you can use it without qualifying with a namespace uh, colon prefix. And then you also may use that using keyword to define a alias type. Okay, let's say you have an int or long, you want to name it something else, whatever you want. Perhaps you give it more of a meaning in your particular application. And this identifier becomes the alias of that type. And then it looks like an assignment operator here, right? So it's pretty intuitive to understand. Um, This is preferred to the C style type def, if you know what type def is. And then there's actually another example I wanted to show you that is basically illustrating the scope and lifetime rules. And so we actually have seen the example there. We can run this program, by the way. So let's just run it. I already compiled it. You just use the B command to compile. Now, see, so that's kind of stuff from here. You got 3 global variables here. Some of them are initialized, some of them not initialized. And now watch out for the ones that you're not initializing. And typically we recommend that when you declare a variable, always initialize it. Don't rely on the default behavior compiler, which can be different depending on what compiler you're using. So you're not really sure. There's cases where the standard defines what the behavior is. There are cases that it hasn't. So so here in this case, for example, the default rule will say this will be initialized with 0. The compiler will do that for you. But it's actually better if you just initialize it yourself like this, right? You put a empty braces and then that's a 0 initialization. Now, in this main function, so this is the function, right? So the function scope, this is actually a block, right? The function, the body defines a block. And this is a block scope. And Inside that scope, you can now, let's say we define a couple of automatic variables, right? Automatic variable, these are the variables allocated on the stack. And if you have them declared as the same name as global variables, they will basically shadow the global variables. The global variables will not, this takes the precedence, the one that you define locally. So if you print out the count 1, it's going to be 10 instead of the global variable's value. And what if you want to access the global variable count 3? Since you already have a local variable count 3, and then you can do that with the global namespace, which is empty, and then colon colon, right? You know, you're familiar with std colon colon because that cout is defined in the standard namespace. In the global namespace has no name. So you still use this namespace, well, still use the scope resolution operator, colon colon, and then that will give you access to explicitly to the global namespace. And now this braces starts a new block, okay? And then so this count 1, count 2, again, that takes precedence over whatever is defined outside. So if you print out a count 1 here, it's going to be 20 here, okay? Not anything outside. You can still access the global, remember, with that colon colon, the global namespace, this way. However, here's the thing. Can you access that count 3 if you define a count 3? Well, actually, you see count 1. Actually, let's go back to count 1. This count 1 here hides the outer count 1. There's actually no way to access that count 1 right away. That's in the in this block scope, but there's no mechanism to access that. But you do have a mechanism to access the global variable. That's count 1 as well. All right. So the rest is pretty much the same stuff. You can go over this if you want, but you know, outside of the scope, you cannot access. For example, here, say that you have defined a count 4 in this inner scope, the block scope, but then you want to somehow access it outside. No, you can't. Okay, this is an error, compile error. Okay, that's what I have to show you for this chapter 3. Thank you.